So let's recap the things we found out last time. Here's a summary of all the dice probabilities that you might compute. We did 7, we looked at 6, you could look at 2. You just count how many boxes there are that correspond to that sum, and then you just add up 136 for each box, and you get this pattern of values: 1, 2, 3, 4, 5, 6, 36, 5, 4, 3, 2, 1, 36. As you count up those squares, as you go, end up going diagonally like this. So 1, 2, 3, 4, 5, until eventually you get to the top. Straight across the diagonal 6, then 5, 4, 3, 2, 1. Kind of fun. So we can call that a discrete probability model. A discrete probability model has 3 basic components: a finite or countable number of outcomes. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 outcomes. Sometimes there can be an infinite number of outcomes, but you have to be able to count them. So just countably infinite, something corresponding to the positive integers would make sense. Secondly, there has to be a probability assigned to each outcome. So we did that here. Here's some probabilities. How do you know it's a probability? It's between 0 and 1. To be a probability between 0 and 1. There could be 0 and it can be 1. There can't be too many 1s, as you'll find out in a minute. The sum of those numbers has to be 1. So if one of them's a 1, the rest have to be zeros. So if we add all these up, you'll find that the sum of all these, 1, 2, 3, 4, 5, 6, 5, 4, 3, 2, 1, adds up to be 36. And so the sum of those fractions is 36 over 36, which is 1. So we met all the requirements to be a discrete probability model. So why does it have to add up to 1? This is supposed to be a list of all possible outcomes. The sum of all those probabilities, if that's everything that can happen, should be 100%. Any model satisfying these 3 components would be called legitimate, meaning it does not violate any rules of probability. But that does not mean it applies to the situation at hand. So there's many possible probability models you might design for dice. And that's a pretty complicated situation. Let's just look at a simple situation of rolling a die one time. And here is something that what you'd expect to happen. This is the equally likely version of rolling one die. Each of the 6 spaces is equally likely, so each of them has 1/6 as the probability, like that. But you might be able to design a die that comes up to be a 1 or a 6, a lot more likely than 2, 3, 4, and 5, so it has some equally likeliness to it. And one way to do that would be assign probability 3/10 to these 2, and then 1/10 to these, so that the total still becomes 10/10 or 1. And that would be legitimate too. So legitimate basically refers to the fact that you might be able to design a machine or a die that could have those probabilities because they're all probabilities that show up. They're legitimate probabilities. They're between 0 and 1. The sum is 1. So it's possible that you could design some mechanical system where those are the chances of the phases happening. So you might be able to weight a die to make this happen. I've done a lot of work trying to weight dice to make a 1 come up or make a 6 come up more likely than the other ones. It's quite difficult to do. If you unbalance the die too much, it's so obvious it's weighted that it doesn't work. And if you don't make it obvious, then when you roll it, it comes out pretty well equally likely. So that's the reason I guess probably dice have survived that long as in games of chance. It's hard to make a die that's unfair and not have it be obvious it's unfair. So sometimes what people will do is they'll make a die which is fair, and they'll change the way that the pips are distributed around the die, maybe to put 2 1s and no 6 on there. So you replace one of the 6s with a 1, and then you might be able to use that, swap it out with another die that goes with it. That one has 2 1s, not 2 6s, the other one has 2 6s, not 2 1s. And that would make 7 a lot more likely to roll. I think people might notice, but if you want to cheat, maybe that's a way. It's going to be pretty hard to cheat by weighting the die, but you might be able to cheat by relabeling it. You get caught, though, you're in jail, I think, so I would recommend against it. We can call our approach, which uses equally likely outcomes, so assuming this type of information, we assumed equally likely in a more complicated way here. with rolling 2 dice. We'll call that the classical method. In the classical method, the probability of any event is the number of outcomes in the event divided by the total number of outcomes. And that's because if each has the same probability, each contributes 1 over n, where n is the number of outcomes to the total probability. So you have 1 over n added up, the number of times of the number of outcomes. So that's the number of outcomes times 1 over n. And that's the same thing as the number of outcomes divided by n. That's the classical method. So in dice, people say the probability of heads is 1/2. You said get 2 outcomes, it's one of them. So 1 divided by 2 is 1/2. You're assuming that the tossing a coin produces equally likely heads or tails. So some people say as long as there's 2 outcomes, each of them is equally likely, like you're playing the lottery, the chance you win and the chance you lose should be equally likely. But you know that that's not, the lottery doesn't have equally likely outcomes. The chance of winning is a lot less than the chance of losing. So just because there's 2 outcomes, winning and losing, doesn't mean they each have probability 1/2. You have to have equally likely outcomes to use that fraction to represent probability. Okay, we're making progress through probability land. We're going to look at assigning probabilities to to tossing 3 coins in a minute. I was going to put it here, but there's just not enough space to do it justice, so we'll stop this one and start a new one up with the 3 coin toss count number of heads experiment.